Introduction to Selection Sort. Welcome to our lecture on selection sort. Selection sort is a fundamental sorting algorithm that embodies the straightforward principle of repeatedly selecting the minimum or maximum element from an unsorted section and moving it to the end of the sorted section. So you can think of a pile of books that you're trying to organize by weight, uh, with the heaviest at the bottom. Then you'd naturally start by picking out the heaviest book and place it at the bottom, then repeating this process with the remaining lighter book. So this method mirrors the core process of selection sort in the realm of sorting data. Here's like an actual selection sort example. Uh, so the problem goes like this. Consider you have a set of books with weights 5 kilogram, 3 kilogram, 4 kilograms, 2 kilogram, and 1 kilogram. You start by finding the heaviest book, 5 kilogram, and placing it at the bottom. Next, you find the 4 kilogram book and place it above the 5 kilogram, and so on until the lightest book, 1 kilogram, is placed at the top. So this is more concrete example based on what I talked about in the previous slide. And here is a selection sort code pseudocode. If you want to do this, so you have an array, and for each index I in array, you will assume there's a minimum index I, and then for index j from I plus 1 to end of array, you'd uh, look at element at j, less than element at minimum. If it's less than element at the minimum index, you update minimum index to j, and then you want to swap element at I with element at minimum index. To understand how selection sort works in Java, here's a selection sort. So you would pass integer array as parameter, and then you would create a for loop with I being 0, and you would iterate until the length of the array, and you would initially set minimum index to I, and there will be another for loop uh, kind of declaring j, and j will be I plus 1, and j will go on until array length, so it will iterate through the end of the array. And if the value of an element of an array at j, if it's less than um, the element value in minimum index at the time, you will update minimum index to j. Because we want to swap these elements, we would temporarily assign the value of element at minimum index to temporary value, and then we will set uh, I as a array in minimum index and set array I as temp, which is the array value of minimum index. So similarly, you would do the same with Python, but the syntax is a little different. So you will use range, and then have set minimum index to I, and similarly you'll have another for loop. And one really good thing about Python is you can swap elements in one line. So now let's kind of dive into the computational complexity of selection sort, it is really important to understand, although selection sort is simple, I would say the selection sort is not the most efficient for large data set. The algorithm's time complexity stands at O of n square in the worst case, as you saw in code example. We have the nested loop structure where n is the number of elements in the array. This means that for each element, the algorithm scans the remaining elements to find the minimum, leading to a quadratic number of comparison. So now let's talk about space complexity. This is where selection sort shines. Uh, Selection sort has O1 space complexity. As you can see in the code, the sort can operate in place without the need for uh, additional storage, making it a very memory efficient choice. However, it's important to note that selection sort is not a stable algorithm. Uh, we talked about stability in the introduction to sorting. To kind of recap, it refers to the preservation of the relative order of equal elements. So in the case of selection sort, equal elements might be reordered, which can be uh might be okay for some situations, but this might not be desirable in some applications. So to understand this stability more, let me give you a concrete example. So you can kind of think about organizing a deck of cards by face value, where each card uh, also has a unique design. Then a stable sorting algorithm would ensure that cards with the same face value are kept in the same order they were originally in based on their design. Selection sort, on the other hand, might mix up the order of cards with the same face value, therefore not preserving their original sequence. Lastly, let me walk through a detailed example of selection sort using a small array. Small array having 5 elements, and the first element being 29, second being 10, third being 14, fourth being 37, fifth being 13. We're gonna sort this array in ascending order, step by step, to illustrate the selection and swapping process at each iteration. So as we can see, the entire array is unsorted. The first element we will examine is 29. And with this in mind, we search the rest of the array and we find that 10 is the smallest. So we initially set, since 29 is I with minimum index, uh, J immediately we find is smaller. So we will swap 10 with 29. So this would result in this array in the second row, 10, 29, 14, 37, 13. And then we would consider 29 and find the 13 as the next smallest in the unsorted portion right here. So we would want to swap 13 and 29, and this would yield this array 10, 13, 14, 37, 29. Then we will need to compare, then we'll need to kind of move to 14. So when we are in 14, we already find that it's in the correct position because 14 is the smallest in the remaining unsorted portion. Then finally, we'll have to compare 37 and 29, and we find that 29 is smaller than 37, so we will need to swap 37 and 29 to achieve our final sorted array, 10, 13, 14, 29, 37. So through this iterative process, selection sort successfully organizes the array in ascending order.